morning to all of you. In this particular lecture, we will talk about the WAMS applications. If you will see that nowadays we are using wide array monitoring based system for different applications like for the generation sector, for the transmission sector, for the distribution sector. And if you see this particular slide where I have just mentioned about the different sectors, like if we take generation, here we can go for generator operation, status and monitoring. Let us say in particular generating station we have large number of like generating power plants, I mean more number of generating power plants, and we have to monitor the corresponding voltage, frequency and the current output, power output. So, there are many parameters which are basically they require monitoring system, what is their status. So, for that purpose of course, we can use the WAMS application like wide array monitoring system. The second one is the transient angle stability. In case of generating stations, we have like different stability issues, voltage stability, then we have angle stability, we have frequency stability. So, keeping on that mind, different type of stability issues can also be monitored using this WAMS structure. Now, coming to the transmission part like state estimation, load flow, optimal power flow, load forecast and economical dispatch. So, these are different operating parts, operational parts of the transmission system, then how to basically help the load flow, the conventional load flow, conventional state estimation process. So, there also we can embed the information from the WAMS technology and we can improve it to a higher version, where this thing will be more realistic and more accurate and more reliable for further process. And this one is also very important, like load forecast. If we can forecast the load pre-hand, like what is happening, how much power we have in our hand next 1 week or 2 days or 1 day ahead, then in that case we can go for the power dispatch, how much power we can supply to that particular customers or to that particular area, that can also we can decide easily. And also we can do the economic dispatch part. Coming to the distribution part, we have like substation automation, feeder automation and the customer side automation. And this is in fact the distribution part is the customer's end, where the utilization of the power takes place. And obviously, the more interaction is going to be at the customer side, and that is why this smart grid aim is to improvise or to make the distribution system more smart in nature. And lot of applications are lying down where there is a great scope if we can apply this WAMS technology for the distribution side. And it is already tested for the transmission side, where we are just placing the PMUs for just transferring the data to the PDC, that is the we have already discussed the data concentration centers, and then it is going to the national PDC, national level data concentration centers, and there from there we can take any decision we like. But in the distribution side also we have to take care, and the same technology can be applied for accurate and reliable operation of the distribution system. Coming to the first part, the substation automation part, the first component is the service restoration. See, sometimes what happens after the fault inception, we have to reconnect the circuit to the main circuit, or we have to basically bring back the service should be restored, so that the customers will get supply after certain time period. So, those type of service restoration techniques can also be improved using this WAMS technology. And the second one is the bus voltage control. At certain buses we could see that the voltage profile is going down, or the voltage is going to be collapsed due to the lack of reactive power compensation or reactive power supply. So, those remedial controls or remedies we can act from the WAMS technology. So, that is what we can control this bus voltage and the line drop compensation, also we have this automatic reclosing facility. So, this automatic reclosing facility also we can draw from this WAMS. And coming to the feeder automation part, we could do this automatic feeder switching, then this feeder voltage control, and again also we have this facility active reactive powers control. So, this active reactive power control is very important as far as the feeder automation is concerned, where the load changes time to time. The load is not static in nature, it is dynamic in nature. So, in that case obviously the active reactive power is going to be changed, they are going to be changed. So, that is why this feeder automation part, this voltage control, active reactive power control are important. Customer side automation, we have advanced metering infrastructure and automatic meter reading. So, these two are already we have discussed in our during our substation automation part, that what is this advanced metering infrastructure. Using this infrastructure we can monitor, basically measure the power at the customer premises for further analysis. This is how this automatic meter reading also does. Now, I will just show some examples that how this particular WAMS technology helped to us. How this particular WAMS technology helps to us. The first one, if you will see, the loss of synchronism. What is the meaning of loss of synchronism? That in a particular network we have 2-3 generators, and if the generator is going out of order due to certain problem or some fault or some maintenance, so or some other difficulties, so the generator is disconnected to the network. So, that condition is known as loss of synchronism. Now, that by taking the voltage magnitude and phase angle information, we can always say that what is the status of this generator, whether the generator is connected to the network or not. So, that is what the technology, this WAMS technology will help to us. Now, we have also this reactive power shortage. If any at particular bus we do not have sufficient reactive power to supply to that particular the bus to maintain the voltage profile. So, always we can send some control command from the control center to enhance the reactive power supply by switching on certain reactive compensation devices, and that is it is quite possible using this WAMS technology. And also we can always by this corresponding, as I said, by looking the voltage profile of each bus, we are just monitoring time to time just in real time platform using this WAMS technology, then always we can see the voltage profile whether it is going to collapse at certain buses in the network. That is what this voltage collapse status. And also we have heavy loading practice. If in some areas we have excess load which are now connected, and this load is basically the load is drawing huge amount of power, then that is known as heavy loading of the network. So, that due to that we may have some oscillations, that basically in a power network when the load increases or decreases, it means the electrical power of the generator decreases or increases. But keeping in mind that at that condition our mechanical input to the generator remains constant. So, as you know that if the mechanical power remains constant and the electrical power varies, so obviously there will be a change in these two powers, that is Pa is equal to this Pa is equal to Pm minus Pe, that is our accelerating power, mechanical power minus the electrical power. So, this accelerating power accelerates the rotor of the machine. So, due to that we may have some oscillation in the current and voltage waveforms. This is what it is shown here in the power. Finally, the power will also oscillate. So, those kind of inter area oscillations between two areas or within a single area we could have some oscillations at different buses. So, those oscillations always we can tap from the wide area monitoring system, and we can take corresponding remedies or some control actions we can apply. Now, coming to this transmission corridor congestion. So, if we are supplying some power, so through the particular transmission line from one bus to other bus, so that there is a chance that that particular line may be overloaded. So, that may be some congestion. So in that case how to maintain it, how to divert the power, unless until you know the status of the line, so we cannot take any decision. So, that particular decision can be taken from the WAMS technology. Now, we have another factor, that is cascading outages, we have frequency deviations, already we have discussed loss of generation. So, these are the focused areas where this WAMS technology can be basically utilized, or I can say in other word, it can be like properly justified, and we can exploit this particular technique for our betterment or better operation of our network or smart grid system. This is one snapshot that WAMS application for phase angle monitoring, that you could see here that there are two buses, we have placed PMU 1 and this 2. So, for that particular one PMU, the voltage magnitude is 239.63 and angle is 0 degree, and this is the phasor position, if you could see in this this circle. And here the second part, the voltage, here is the magnitude is 235.85 and the angle is minus 15.0 degree, and here is the phasor position. So, phasor means it has the phasor word itself indicates the VA. If it is a phasor voltage, then it has a voltage and also it has an angle phi. That is what this voltage VA is 239.63 kV and the angle is 0 degree, and here is this phasor position. And when this angle is minus 15 degree, so this angle is basically minus 15 degree. So, this is how we can take the snapshots from the wide area monitoring system technology, and easily we can locate where is this particular phasor is lying. We can see always the phasor position of particular bus of a particular power network. Now, if we will come to the WAMS application like voltage stability monitoring. Here also we can see from the wide area monitoring system that if it is green, it is a basically normal operation of the system. That means the voltage is in a stable condition. If it is like yellow, it is a early warning condition. Now, if it is red, it is emergency alarm system. So, these are basically the symbols or colors we use to detect whether my system this voltage is stable or it is in unstable mode. So, of course, if this is the condition, so we can take some control measures or control actions. That is what is our target. First of all, we know what is the status, then we can take the corresponding actions. Now, this is this power oscillation monitoring part, and if some areas like between two areas, the tie line basically connects two areas. If any oscillation occurs within this tie line, so we can monitor from this wide area monitoring system facility. So, from there we can take some decisions. These are some examples I said. So, there are a lot of many applications we can do from this wide area monitoring system structure. Now, already we have discussed when I started this wide area monitoring system lecture, that we have discussed that there are three components of this wide area monitoring system. The first one is the data acquisition, second one is the communication part, and the third one is application. So, already we have seen application part. As for the data concerned, we have already discussed the synchronized measurement data, that is the operational data, and other part is non-operational data. Those non-operational data we can obtain from this one of the device. This is the digital fault recorder. It is known as DFR. So, what are the, this is the basic block diagram for this. We will accrue the signal, and we have expert system, and from the expert system we can store the data or we can process the data for further actions. So, it will just this digital fault recorder acts as a black box of a substation, and it records highly accurate waveforms related to the faults. It will record, it basically records the voltage current waveforms during the fault inception period. So, it will just say at what accurately at what point the fault was there. The fault was incepted in a particular line or in a particular device or transformer, generator, or you can say feeder, or so any load, so wherever. So, we can always record the voltage current data using this particular device. And this the recorded data, huge amount of analog and status data for pre-fault, fault and post-fault conditions can be also used for further analysis. that particular device will help us. Now, we have another device, that is the digital protective relay. We will discuss more about in our subsequent classes when we will talk about I will just take about the protection part of the smart grid system, that this digital protective relay also takes a very good decision, and it will just try to protect every equipment, in fact the generators, transformers, transmission line, feeders, loads. So, every equipment basically protected by one digital relay, and this relay digital relay takes the voltage current information, and it basically operates with certain signal processing techniques, and it gives the trip signal to the circuit breaker. And also we have third one, that is a circuit breaker monitoring device. It will just this particular device, this monitoring device will monitor the status of the circuit breaker which is present inside the circuit. It may be in the transmission level or it may be a distribution level. So, we can always extend, even if suppose it is related to the distribution level, always we can extend this technology to other level also. So, to facilitate the smart grid technology, and also to have a better visualization of the circuit or network for understanding what is happening inside the circuit, so that any disturbance, any event is going to be happened inside the circuit. So, we can take some major action before going to have some cascading failure of the circuit or some blackouts or brownout. So, in that case these devices data which are obtained from these devices are very important. I will just come to the very important part of this wide area monitoring system, that is a Phasor measurement unit, and in fact this PMU is the heart of our wide area monitoring system. So, without this PMU the wide area monitoring system has no meaning. So, this PMU stands for Phasor Measurement Unit, and basically as the name suggests that phasor, it measures the phasor of the voltage and current. If let us say these are two buses where we have this V1 is the voltage magnitude or phasor of bus 1, and this V2 is the voltage phasor for bus 2. Now, how to know this phasor position of these two buses? As already we have discussed, in the SCADA system the magnitude of the voltage of each bus basically is known to us, but not the phase angle. But nowadays if you could see our distribution system or even the transmission system or network or distribution network are becoming basically from passive to active network. Why? It is why? Because due to the integration of renewable sources like small hydropower plants and wind turbines or solar system. So, this network is becoming now from passive to active. Now, the distribution system is also having the facility to generate the power from any corner of it. That means, because we are connecting the solar and wind small hydro stations at nearest to our load terminals. So, we are generating the power. So, in that case with magnitude information, it is not sufficient to visualize, to control the network or to protect the network or the smart grid system. So, it is necessary to have this both the information like magnitude of the voltage and angle of the voltage, or maybe the magnitude and angle of the current. So, that is what this PMU device helps to us providing this magnitude and phase angle of the voltage and current. If this is basically the bus 1 phasor, this blue one. So, this is my V1 phasor position of the voltage, and this red one is the phasor position of the V2, that is our bus number 2. And we have a very good facility that with the advancement of these computer facilities and also signal processing techniques, we could we are able to estimate the phasors of the voltage and current in real time platform. We use basically the DFT, discrete Fourier transform, for this, and the inside the PMU the algorithm runs, and using that we can always estimate the phasors of the voltage and current for further analysis. And that is how this phasors notation or phasor positions we can always obtain using this PMU device, which are basically installed inside the power network. Now, this is one of the PMU connection snapshot, where this phase conductor, this is our phase conductor or the power conductor, and this is our potential transformer, and this is our current transformer, and here is our PMU, the Phasor Measurement Unit PMU, and this current transformer is connected to the PMU terminal through this burden, and we have also this instrument transformer which is also connected through this attenuator to the voltage terminal of this PMU device, and we have always this computer is connected to the interface to the PMU to analyze the data and what are the voltage current phases or instantaneous values, or even sometimes this PMU also, if it is customized properly, it can also record the frequency and the rate of change of the frequency. So, this computer basically records or it displays the voltage current data. Now, this is how this I will discuss about the PMU scenario in India, that we have different SRLDC means southern part of this load dispatch center, and this is our eastern region, this is western, this is northeast, and this is northern region. And we have total 5 load dispatch centers, and at every load dispatch center we have PDC, the phasor data concentrator stations, and from there the data are just passed to our national load dispatch center, that is we have a national PDC. So, where we will just receive all the PMU data from all the national grids, 5 national grids. And we have also PMU pilot projects are upcoming, and is also some PMUs are installed, it is also in operation, and Government of India also planning for more PMU installation in our transmission network. And if you see this PMU scenario in eastern region, these are some of the data we have collected: Rourkela, Jaipur, and Raigad 2, the current feeder connected to PMU, and Talcher 1, and Durgapur, Rangali, and these are some places, Ranchi, Jamshedpur. So, we have the eastern region. So, these are the places where we have the PMU connection. Similarly, we have northeast region where the PMU connection also there, and this is for the northern region part. This is our Dadri, Kanpur, Agra. So, these are the places where we have PMUs at 400 kV bus system. You could see here the bus voltage is 400 kV, and similarly for the southern region also at the 400 kV level we have installed the PMUs for our further processing, and this is for the western region. If you could see that more or less India is also progressing towards this WAMS technology, and in near future we will also extend this technology towards the distribution sector, to the distribution part, so that our whole network will be smart, both transmission distribution together. Now, I will just come quickly again to this PMU part, how it measures the synchronized data, the synchronized phasor voltages and currents. Now, this is one location in the network, this is location 2, that these 2 locations are apart from each other, but still at the control center the data, the voltage V1 from this location, the phasor, and V2 the voltage data or voltage phasor will get from location 2 will be in same time stamp. So, for analyzing this 2 data we need these 2 voltages should be synchronized, then only we can analyze, otherwise it will be difficult to analyze these 2 phasors. So, that particular work is done in WAMS technology using the PMU device. Now, the angular difference between these 2 can be determined if the 2 local clocks are synchronized. See, here also we have one local clock, and here also we have one local clock. So, if these 2 clocks are synchronized together, then only these 2 phasors can be compared together. That is what the meaning of synchronized measurements. And this synchronizing pulses are obtained from the GPS satellite. The GPS satellite will supply the synchronizing clocks or synchronizing pulses. So, with help of which these 2 phasors are going to be coordinated or going to be synchronized at a common time frame. And if we are just synchronize the time stamp, if we have like the angle of 360 degree, here it is, and our sampling basically if it is 1 millisecond base. So, what is the angle between two corresponding samples? It will be 360 degree divided by 20, because we have 20 milliseconds within 50 hertz one cycle signal. So, this 20 milliseconds. So, if you divide, so within 1 millisecond, so it is going to be have 18 degree between two samples, two corresponding samples, the angle difference is going to be 18 degree. And if you just correspond to 1 microseconds, how much it will be? So, it will be if you just divide again 10 to the power this 3, so it will be 0.018 degree. So, the precision is better, the resolution, I mean if suppose we have some error between two samples. So, if we take like 1 microsecond resolution, so it will be much better here than this 18 degree difference. So, these are the concepts of synchrophasor angle measurement. So, this 1 pulse per second 1 ppс corresponds to this t equal to 0 when this cosine function is having the peak value. This is what the definition by the IEEE standard, that how to standardize this synchronized angle. Universally this angle should be synchronized. Then for that we have some format, we have some standard, like we have to take one cosine function, that is what here this phi, this is, if this is my signal, this phi is the instantaneous phase angle relative to a cosine function. This is our cosine function, this is our cosine function at a nominal system frequency, that is our 50 hertz signal frequency, synchronized to the universal time coordinate. This is important. So, if I will get the pulse 1 pulse per second from the satellite, from the GPS system. So, in that case, so if it is at t equal to 0 at the peak value, so then in that case my phi is equal to 0, because it starts from 0. And how to write this particular phasor? This I max or x max divided by root 2 angle of 0 degree. X stands for either voltage or current. It may be a voltage signal or it may be a current signal. Now, if suppose there is also another part, this angle is 0 when the maximum of xt occurs at UTC second rollover. Now, and minus 90 degree when the positive 0 crossing occurs. If suppose let us say this particular peak is moved to this point, that means what is the difference between the phase difference between these 2 points? 90 degree. So, this point is lagging to this point by minus 90 degree, it is lagging by 90 degrees, see here. So, this is our 90 degree, that means this point is lagging to this point by 90 degree. So, while we will express this particular instantaneous signal in phasor form, so we will write this is the magnitude and this is the angle part minus 90 degree. So, we have basically standardized this using this PPS 1 pulse per second. That should be the strategy to synchronize the voltage current phasors at different buses in a particular smart grid system. This UTC stands for basically the coordinated universal time, that is the primary time standard by which the world regulates clocks and time, and it is within 1 second, means solar time at 0 longitude. So, this is important. Using this UTC concept, we can synchronize the basically if we have different number of buses in a network. So, this V1 phasor, this V2 phasor or V3 phasor, all together they can be synchronized globally. This is basically the basic block diagram of the PMU. We have first the analog inputs. The analog inputs means the voltage current signals, and this voltage current signals will pass to the anti-aliasing filters. We will discuss about this, what is the function of this anti-aliasing filter. Then it will go to the ADC converter, the data, and here still this is analog, this signal is analog here, and even the signal status at the output of this analog anti-aliasing filter is also analog in nature. Now, this analog signal is going to be converted to digital platform using this ADC converter, that is analog to digital converter, and after that this will go to the phasor microprocessor, where the phasors are going to be calculated or estimated using the discrete Fourier transform technique. Now, after that it will go to the modems for communication purpose to the PDC, the phasor data concentrator, and from the phasor data concentrator we can apply to other devices like relays or some circuit breaker, wherever we like to utilize the PMU data we can always apply. And this is how the other part this is our global positioning system, that is GPS. We have the global positioning clocks like 24 satellites on 6 orbits at a height of 10898 miles, and each satellite covers 42% of the globe. We have 6 orbits and 24 satellites, and this satellites rotates around the earth, and it will just the GPS receiver will receive the signal from the satellite and it will just supply to the phase locked oscillator. So, this phase locked oscillator will generate or it will lock the sampling frequency according to the GPS receiver signal. 1 pulse per second will be received by this satellite, this GPS receiver, and it will send to this unit, and from there this ADC will start sampling the voltage current signal, and then it will send to the processor. This is what the word sampling at 1 millisecond. Let us see, we will discuss about the sampling part. If we have voltage waveform, then for relaying purpose, for protection purpose, the sampling rate is basically step side we took basically 1 kilohertz, 1 kilohertz. That sampling frequency we denote by Fs. This Fs is known as sampling frequency. Now, if the sampling frequency is 1 kilohertz and we have a 50 hertz signal, let us say voltage signal. So, what is the time period for this particular signal? That is 20 milliseconds. How it is? 1 divided by 50 hertz, because 1 upon frequency is our time, 1 period, that is Ts. So, this fundamental time period is 20 milliseconds, fundamental frequency is 50 hertz, and for this particular signal we are taking 1 kilohertz as sampling frequency. The meaning is we are sampling the analog signal at a rate of 1 kilohertz. So, after every millisecond, 1 millisecond we are getting the samples, the digitalized signal of the analog signal. If you could see this particular signal, we have 1 kilohertz sampling frequency. After every 1 millisecond we have samples. So, overall we have 20 samples per cycle. If you can count here, so we will have 20 samples per cycles. So, we write like this, 20 samples per cycle. So, within 1 cycle we will have 20 samples, within 2 cycles we will have 40 samples, and within 3 cycles 60 samples, so on. Now, if we just take another sampling rate, that is 0.02 by 8, means 8 samples per cycle, and in that case you can see here the signal is not approximated actually to our actual signal. The approximation is less here. You can see here it is better because we are just taking more number of samples within 1 cycle, but here the number of samples decreased. That is why the approximation of the exact signal is not possible. Now, if we increase the number of samples per cycle more, like here we have taken 64 n, we denote capital N. N basically stands for number of samples per cycle. So, if we have increased here the number of samples per cycle to 64, so in that case we have better resolution, better approximation to our original signal. That means to have a better approximation or exact, if you want to extract or we want to convert the exact analog signal to digital, that means we have to increase the sampling frequency. But of course, however, we have some certain limitation for this. So, what should be the sampling frequency so that our signal should not be affected? I mean the digitalized version of the analog signal should be proper for further processing through the microprocessor or DSP processor inside the PMU. During this sampling, or we have one impact, that the effect, that is aliasing effect. This aliasing effect means if a fundamental, basically we have some, let us say 50 hertz signal, but during the power system operation we have like higher fundamental, higher frequency components like other harmonic frequency components, second harmonic or third harmonic or fourth or fifth harmonic components are present. So, those are our higher frequency components. In that case, what happens, due to this aliasing effect, the higher frequency components will behave like a small signal low frequency component or fundamental frequency component. So, that effect is not desirable for relay or PMU operation. So, in that case we have to remove this effect using different concepts. So, if you just if you take a fifth harmonic component which is merged with our fundamental frequency, then in that case if I am sampling at rate of 8 samples per cycle. So, if you could see here, these are the samples we have taken, that is 1, 2, 3, 4, 5, 6, 7, 8. So, here is our cycle ends, 0.02 second means 1 cycle. So, within 1 cycle we have 8 samples present. So, in that case if I just taking this 8 samples per second, so this particular fifth harmonic component of the signal will behave as just like I am the fundamental frequency component. So, please take me. So, in that sense the aliasing effect is severe here. So, we have to remove this. So, what we do for this case, we basically do, this is one more example. I just want to also explain this waveform, that this particular waveform is having 660 hertz frequency component, and if you are just sampling this particular waveform at a rate of 6000 hertz per second. So, we will get the signal like this here. So, this particular waveform will behave just like a 60 hertz component signal. This signal will behave just like a 60 hertz signal component. That means, this high frequency component will behave like a small frequency component or fundamental frequency component. So, this effect is known as aliasing effect. To overcome this particular problem, we have anti-aliasing filter. This anti-aliasing filter, first we maintain one theorem, that is sampling theorem and Shannon's theorem. What we have to do? We have to maintain the sampling frequency in such a manner that it should be greater than twice of the higher frequency component of the signal. Let us say we have certain high frequency component which is present in a particular signal. So, our sampling frequency should be 2 times of that particular signal. It should be greater than that or equal to that. So, in that sense we can overcome this aliasing effect. That is what here this sampling theorem tells. Now, also we maintain low frequency like low pass filters, where we will just remove the higher frequencies and we will just pass the low frequencies and also our fundamental frequency for our application purpose. Basically, in this case we use the RC filters, and sometimes you can see that some other low pass filters are also used. Now, this is one specific example where the RC filter is shown, that these are the resistances values and these are the capacitance values, and this is how this gain here present, and this is how 360 is the cutoff frequency. So, there are a lot of research is also researchers are just trying to have this design of these RC filters for removing this higher frequency components when the signal is passing from one domain to analog domain to digital domain. And also next we use the ADC in case of PMUs, and we have different type of ADCs like successive approximation, integrating, flash or parallel. So, depending on their resolution, speed and also noise immunity and cost. So, this is the table how this particular all different types of ADC vary in their operation. And this GPS already we have discussed, that GPS transmits basically 2 frequencies. The first one is 1227.6 and second one is 1575.2, so 42 megahertz. So, these 2 frequencies are the transmitted frequency by the GPS technology. And if you will see that these are arranged in 6 orbital planes and displayed from each other by 60 degree and having an inclination of 55 degree with respect to the equatorial plane. So, there is some certain arrangement for this GPS, so that we can cover the whole network nicely and properly and for our operational point of view. Now, this if you see this PMU gets this sampling clock is phase locked with the GPS clock pulse. This is very important. This phase locked oscillator and the GPS clock together they are locked, then only this ADC will start sampling this analog signal to digital domain. It will just start sampling this analog signal to digital domain. Basically, one question comes here that what are the data or voltage information which are provided by this PMU. This PMU provides positive sequence voltage and current also. Now, if we have inside the PMU, we have discussed that we measure or we estimate this voltage like VA, VB, VC phasors using the DFT, the discrete Fourier transform technique. By using this phasors, so we can always calculate the positive sequence component of the voltage, that is VA plus A VB plus A square VC. So, this positive sequence component of the voltage can be estimated or calculated inside the processor of the PMU using the phasors of corresponding voltage signals, instantaneous voltage signals. And it is also possible to measure the local frequency and rate of change of the frequency. This is also important. First of all, it provides V1 I1 positive sequence voltage and current, and second one it provides the frequency and also df by dt, the rate of change of frequency. And the third one is very important. If it can be customized, so it can also measure or provide harmonics. This is very important, because nowadays in smart grid system we have many inverter based generating stations, it is coming up, basically solar, wind, or we have fuel cell, or we have like other devices where we have electronic devices or electronic interfaces are present. So, in that case there is a good chance of harmonic injection to the network. So, for that this PMU can be customized properly to estimate the harmonic components of the voltage and current signal, and also it can provide V2, V0, that is the negative and 0 sequence components of the voltage, and also I2, I0, the negative and 0 sequence components of the current. So, these are the output data or the output information we got from the PMU. This is how this PMU transfers the voltage current signal, and this is the GPS receiver. Time is synchronized, at what time we want to start the sampling of this particular signal, and after the getting this sampled values of the voltage or current, we will apply the DFT to estimate the phasors, and we will get the symmetrical component transformation technique. Using that we will get positive sequence components, and further also we can get negative and 0 sequence components, and then also we can calculate the rate of change of frequency, and further we can apply for the real time application or some disturbance or transient recurrence, whatever the applications we want to do, we can do using this data. This is how this sequence components are calculated, already we have discussed here, and this is the single phase reporting rate. This is for 50 hertz 10 samples per cycle, 25 here, 50 here, and for 60 hertz these are the figures. This is the IEEE standard basically. And this is the basically the file structure of synchrophasor standard, the header file, the configuration file, data file, and command file. So, these are the files which are present inside the PMU, and those files, the data file are sent to the PDC. We have already discussed how this data file are sent to the PDC for further application, that the PDC will basically provide one command that you send the data file, then the PMU will be triggered and it will supply the data files to the PDC, and then the PDC will again send one stop file, then the PMU will stop the data from the PMU to the PDC. These are the formats. This is one PMU kit, and in Indian context within 4 to 5 lakhs also we can just purchase one PMU for our network application. So, in this particular class we have discussed about the wide array monitoring system applications, and then we just started with what are the application areas like to monitor the angle variation or stability issues or angle oscillation also. And after that we just discussed the PMU part. The PMU is also important component of the wide array monitoring system, where we have discussed how this data is basically synchronized and data are passing from one PMU station to other stations, and what is the GPS clock does and many other parts. Thank you all.